Good evening, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 12th problem from the Project Euler problem archive. So this problem asks us to find the first triangle number that has over 500 divisors. And you may recall from a previous video that the nth triangle number is just the sum of the first n natural numbers. And so it gives an example here that the sum of the first 7 natural numbers is the 7th triangle number, 28. And we have an expression for the triangle numbers that we derived in a previous video, and that's n times n plus 1 over 2. And I'll link to that video in the description if you're curious. Now there's also an expression for the number of divisors of a natural number. And we have not yet looked at that expression. And so we're going to get into that now. So as usual, let's copy our template directory to make our problem directory. And we'll open our analysis file. So let's start with the fundamental theorem of arithmetic, which states that any natural number n can be written uniquely as the product of prime numbers. So we might, for example, write n as p0 to the a0 times p1 to the a1 times p2 to the a2, dot, dot, dot. And then suppose we have some divisor of n, call it d. Well, this is a natural number which also can be factored similarly. So we might say, d is equal to similar expression, but with exponents of b0, b1, b2, etc. And I'm going to claim, without proof for the moment, that d is only a divisor of n if, for all I, bi is less than or equal to ai. And so this suggests an approach to counting the number of divisors. If we look at a particular prime, say p0, we could consider all the possible values of b0 that are less than or equal to a0. And it's just going to be 1, 2, 3, 4, dot, 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 all the way up to and including a0. But then also 0 is a possibility. And so there are a0 plus 1 possible values of b0. And you can make a similar statement about the possible values of b1, the possible values of b2, etc. And then the total number of divisors is just going to be the product of those terms. So that is, we'll say, numdiv of n is just equal to a0 plus 1 times a1 plus 1 times a2 plus 1 times dot, dot, dot. And I'm glossing over some of the details of this analysis. This is certainly not a rigorous proof. But I really want to get into the problem itself. And so what I think I'll probably do is to release a follow-up video where I'll dig it a little bit more into this analysis for those who are curious. But in any case, for now, if you take my word for it, we have an expression for the number of divisors of n. And so this will allow us to solve our problem. We'll start by considering the first triangle number, and then we'll consider each triangle number in increasing order until we find the first one with over 500 divisors. So let's start writing some code here. So we'll want a method for calculating the number of divisors, essentially implementing the expression that we just described over here. So we'll say count divisors. And you might think that like you might as your first thought on how to implement this, say like, okay, well, we've got some maximum, max num primes equals 30, I don't know, and then we're gonna say primes is gonna be max num primes, and then we've got uint 32t exponents max num primes, and like we go and we figure out this full prime factorization, and then we can calculate our number of divisors. But it turns out that this is all actually unnecessary, and that's because we don't need to know the exponent. We don't need to know every prime divisor and the exponent on every prime divisor at the same time. We only need to know the first prime and the first exponent, and then after that we need to know the second prime and the second exponent, and then after that, etc., etc. And so, and in particular, we can, when we know the first prime and first divisor or first exponent, we can calculate this first term and multiply that with our running total. And then when we know the second prime and the second exponent, we can calculate this term and multiply that by our running total, and so on. And so we actually don't need to do the full prime factorization. And so we'll say, let's suppose the current divisor is div, the current exponent is exp, and our running total is count. Now you'll notice that because we're multiplying for our running total, we want to start at 1. That is, if we were adding values to get our answer, we would want to start at 0, but we're multiplying, and so we want to start at 1. For our divisor, we want to be careful to start at 2. If we were to start at 1, you'll notice that that n is infinitely divisible by 1, and so we would just get stuck in an infinite loop. And so we want to start with 2 as our first divisor. And then our strategy is just going to be to find a divisor of n, repeatedly divide n, and count the number of times it divides. Calculate one of these terms and update our total, and then move on to the next divisor, and continue doing that until we have divided out all of the factors of n. And so we're going to say while n is greater than 1. And so we'll want to start with our exponent at 0, and we'll say while n mod div is equal to 0. Then we're going to divide out. That is, when we find a divisor of n, then we're going to repeatedly divide n by that divisor. So n divide equals div. Each time we're going to increment our exponent. And then after we've determined the exponent for the next prime divisor, then we're just going to say count times equals exp plus 1. And then we also need to increment our divisor. and return count. Now, some of you might be skeptical that this code actually works. In particular, you might see that there's nothing about prime numbers in here. I'm not calculating primes. I'm not checking these for primality. And so how do I know that I'm only dividing by prime divisors and not like some composite divisor here? And the reason is that, like, because we are considering non-prime divisors, like we will get to this line of code with, div is equal to 6, for example. But the key point is that by the time div is equal to 6, we've already considered div is equal to 2 and div is equal to 3. And so we've already divided out those factors. And so by the time we get here with div equals 6, we know that n is not divisible by 6. We used a very similar technique for problem number 2. And so I'll link to that video also if you're curious to see the details of that. And so this code should work just fine. You'll notice that if we come to a divisor that is not actually a divisor of n, then we'll skip over this. Our exponent will still be 0, and this will be equal to 1, and so our value for count will be unchanged. Okay, so moving on to our main function, we're going to want some static const target divisors, and we'll start off with that as 5. If you happen to notice in the problem here, the example input it gives is that 28, the 7th triangle number, has over 5 divisors. So we'll start by trying that. And then we want, uint32tn is equal to, we don't need to initialize that. We need also, triangle and, num divisors. Okay, so let's see. We're going to say for n is equal to 1. N is less than, infinity, and plus n. And then we're just going to say, triangle is equal to n times n plus 1 over 2, and num divisors is equal to count divisors of triangle. And then we'll say if num divisors is greater than target divisors, then we're going to say printf triangle %u equals %u has %u divisors. And so it's going to be n triangle and num divisors. And at this point, we have our answer. We don't actually need to search any farther. We don't have any objects we need to clean up, so we can just return. Okay. Yeah. So I sort of put in a placeholder here for our upper bound. And it turns out that we don't need an upper bound. It's actually legal syntax to just leave this out, which means just keep going forever. In fact, it's even legal to do something like this, which is referred to as a forever loop. It initializes nothing, updates nothing, and will run forever. Yeah, so it's perfectly legal to leave out this second section here. Okay, so let's see if our problem or if our solution works. All right, so it tells us that the seventh triangle number is 28 and has 6 divisors. That is expected. So let's crank this up to 500. All right, and so this is now telling us that the 12,375th triangle number is equal to 76,576,500, and that number has 576 divisors. Now, before we go on to check our answer, there are 1 or 2 optimizations that I feel I would be negligent not to mention. It turns out that they're not necessary. In this case, our solution is plenty fast enough, but I still feel that they are worth mentioning. So in particular, because of the structure of the triangle numbers here, we don't have to calculate the number of divisors for the full triangle number. We can calculate the number of divisors of n, the number of divisors of n plus 1 over 2, and then multiply those together to get our answer. And that's much more efficient than calculating the number of divisors for the full triangle number. For 2 reasons. One is that n is roughly the square root of the nth triangle number, and so we're working with much smaller numbers in that case. But then also because when we're calculating the n plus first triangle number, the expression for that will be n plus 1 times n plus 2 over 2. And we've already calculated the number of divisors for n plus 1. And so we don't even have to recalculate that because we calculated it for the nth triangle number. And so let's add those 2 optimizations. So we'll say left divisors and right divisors. So roughly speaking, this is going to be the number of divisors of n, and this is going to be the number of divisors of n plus 1. There's one caveat to that, which is that one of those will be even, and so will be divided by 2. And so it will either be the case that this is the number of divisors of n over 2, and this is the number of divisors of n plus 1, or this is the number of divisors of n, and this is the number of divisors of n plus 1 over 2. And so with that caveat in mind, we're ready to apply these optimizations. So we'll say, we have our triangle number there, and we'll say right divisors is equal to, we want to say if n plus 1 and 1. You might recall this is just checking for oddness. This is a way of checking to see if this number is odd. So we say if n plus 1 is odd, then right divisors is going to be count divisors n plus 1. And if not, that is if n plus 1 is even, we're going to say right divisors is equal to count divisors n plus 1 over 2. And now num divisors is just going to be left divisors times right divisors. And then when we update, we'll say left divisors is equal to right divisors, because the left term for the the right term for the nth triangle number will be the left term for the n plus first triangle number. And so we can update left divisors from right divisors like this. Now we still need to assign some value to left divisors to start for the very first term. And so the first term is going to be n equals 1. The triangle number is 1. 1 has one divisor, and so we can initialize left divisors is equal to 1. Okay, so let's see if this gives us the same result. Apparently I've made a minor mistake. Looks like line number 46. I just left off an S. Made a minor typo. Okay, we get the same answer, the same result, so that looks good. Our solution is presumably much faster now, though it's not perhaps perceptible. But that said, let's get on to checking our answers. So we'll go back to the archive here, and you'll see that, in fact, our answer matches the expected value. So as I mentioned earlier in this video when we were doing our analysis, I kind of glossed over some of the details a little bit, but I'd really like to do a video where I dive into that in a bit more depth. And so if that sort of number theory analysis interests you, that will likely be in the next video. If you're just interested in the C and C++, then you can look forward to my solution for problem number 13 in the video after that.